Hello everyone, we are Team EDE and our project is comparison of effectiveness of different precoder approaches. Before we dive deep into what we have done in our project, it is reasonable to say about the field of telecommunication and why we decided to work on this project. First of all, telecommunication is used to transfer data between transmitter and receiver. When we use your phone, you're basically exchanging information with base station in one of the possible ways, downlink or uplink. When base stations send you data, it usually goes through a complex pipeline that is shown on the slide. To send signal, transmitter have to use source encoding, channel encoding, and add interleaving with modulation. After that, signal is sent through channel environment and affected with some noise and interference. On the receiver side, this process is reversely repeated. The main goal of communication system design is to maximize transmission rate and system utilization and minimize bit error rate, required system bandwidths, complexity, and required power. Unfortunately, it is almost impossible to satisfy all those criteria without affecting the others. So we have to find a new ground. In this project, we wanted to significantly reduce bit error rate with small increase of system complexity. We started our project with getting familiar with SVD-based MIMO precoding and equalization schemes for realistic channel knowledge, design criteria, and performance evaluation paper. In this paper, authors firstly describe basic approach in telecommunication system that you can see in this slide. We wanted to repeat their result and after that, use this approach for new radio signal DMRS to see how it works. In their paper, authors used SVD-based MMSE and zero forcing as main methods. General idea behind these methods is zero forcing tries to beamform by remove interference by zeroing it, and MMSE do the same but with respect to possible noise. Authors of the paper claim that before them, most of the research on this topic were with ideal channel estimation, which is almost never the real case in real-life scenario. In case of an ideal radio channel knowledge, the SVD-based precoding procedure, which is applied at the transmitter side, is going to consider all possible eigenmodes, which results in a perfect separation of all signals at the receive antenna output and into a minimum bit error rate. But in case of non-ideal channel knowledge and limited accuracy in the channel matrix H, estimation reduced number of eigenmodes in the precoding process will become an optimum and will lead into increased BER performance. Mathematically speaking, we can reduce eigenmodes to reduce BER. Main formula of this process is shown on this slide. After the system complexity will be reduced in comparison with full matrix and BER will be a little bit more. However, this change might be better than simply decreasing complexity with removing transmitting antennas. In case of real channel and set approach, zero forcing SVD and MMSE starts to look like shown on the slide. The main difference is that after we're losing Hermitian property of matrix V because V and V tilde are not Hermitian anymore, therefore received signal will not be ideal and we will have to deal with it later. After this, we started to repeat what authors did during their project, and to do that, we have to consider some assumption and approximation because they were not stated in the paper. The assumptions are that we haven't used full transmission process because they haven't described a lot of details of it. The assumption that they have used 16 QAM modulation because it is one of the most popular choice, and they said that they have used QAM modulation. And in the end, we haven't figured out what is their post-process of SVD approach on real channel because mathematically it looks exactly like zero forcing, and we will back to that later. So we started to work. We started with the following approximation. Let our signal in vector S equal only zeros and ones. In this case, calculating BER was very simple. Just subtract the sent signal from the received one, and we get at least desired decrease in BER with an increase in SNR. At this point, it was unclear how the BER for pure SVD should be calculated because our received signal was represented as singular values multiplied by the sent signal. The first attempt were simply multiplication by the D-inverse matrix, but this was just another form of zero forcing. and the SVD and zero forcing plots were identical. After closer reading, we found some errors in the modeling, and this increased the burr performance at the least for an ideal channel. We also decided to create another rule for calculating the burr of the pure SVD methods. We multiplied our signal by singular values and compared these values. As a result, we get behavior similar to the pure SVD approach presented in the article. And as you can see from the graphs of our zero forcing approach was better than MMOC. Final step, we tried to fix the behavior of the MMOC approach. The main idea was to fix pseudo-inverse computation. In our first attempts, we just used sigma as noise variance, but in this paper, it was a wide Gaussian noise process with autocorrelation noise and with noise variation sigma. This allowed us to obtain similar behavior for the MMOC and zero forcing approaches. And also it was decided to remove the calculation of the pure SVD approach due to some kind of strange calculations. We tried to get the most results from the paper, so we also calculated the distribution of singular values, but again, it was not clear what they meant by distribution. From our point of view, this is probability density function. We get this result shown in the slides, but they are very different from their results. We tried to obtain distribution with fixed SNR for ideal and realistic channels and compare them with their results. Positions are the same, however, density is not the same. The following results show attempts to use eigenmodes. The number k is the number of the first eigenpair that I used in the calculations. In the article they wrote, they specified cross-match to discarded eigenmodes. From our point of view, it is like the last values of singular values equals to 0. According to our results, the first eigenmodes show the best result, since they demonstrate good characteristic of the second eigenmode. With an increase in the number of receivers, performance should also increase. In our case, we get a huge increase in the ideal case, but very small increase in real case. In the final stage of the project, we tried to implement QAM modulation in order to send not real numbers but complex ones because our channel is complex. In this case, using modulation demodulation, we get a slightly worse result, but this model should be closer to the model proposed in the article. In this graph, you can see the comparison of the QAM modulation with previous models. And after that, we tried to use stated DMRS signals. DMRS signal refers to demodulation reference signal. It is a new type of signal that has been introduced in new radio, which is 5G. And DMRS is used by a receiver for radio channel estimation for the modulation of associated physical channel. We wanted to know how this model will work on DMRS signal, since poor performance on this signal may lead to significant overall performance decrease of all the system. In conclusion, we would say that after searching for new papers in the areas of precoding methods, we found that the methods described in the selected article are relevant today, and there are no new articles, at least in the public domain, that we have found that says otherwise. Unfortunately, this work in most cases was related to signal processing, and due to lack of our knowledge of all processing in this area, many simplifications and approximations were made. We have repeated almost most of the paperwork, and some of our findings are not dissimilar. We're sure that our simplification and misunderstanding links to this. However, there might be other cases, and we have to look at this more. We were unable to plot the spectral efficiency of the eigenmodes due to lack of information on how they did this exactly and what approach they have used. We can improve our project with massive MIMO models such as 4 to 64 or others, or with a lot of users that can lead to huge interference. Also, the channel model should be better in terms of approximation and simplifications. We are Aider Frazilov, Denis Lagashov, and Andrei Smirnov, Team ADA, and this is our project. Thank you for your attention.